In my last video, I showed the rebuild of the Stepcraft CNC, and I'm calling that the big one because almost immediately, well, actually, while I was still working on it, I started building a smaller one that I'm going to dedicate to cutting metal mostly and plastic, with the idea being that I would use up the parts that are left over from the Stepcraft CNC. In particular, the rails for the Y-axis that I didn't use in the big CNC. So the first thing that I did was I took those Y rails and I cut them in half. To do that, I had to cut through the hardened steel linear bearing guide with the angle grinder just to give me enough space to get the chop saw in to make the cut. Then I took the aluminum ends from the original machine. These are orange, and I cut them to length, quite a bit shorter than they were, and I put them in the big CNC to start milling those to shape. I needed a new hole for the stepper motor, and the rest of this that I'm doing here is just cosmetic, really, and I wanted to try out the CNC to see how it would cut aluminum dry. Now, one of the problems that I had was that I didn't have enough of those bearing blocks that fit on those hardened steel linear guide rails, because I reused the X-axis on the big machine, and therefore I had to find replacements for those bearings. I looked online, and you can get them in Europe, but the shipping to get them here would be outrageous. So more or less as an experiment, and because I really don't have anything to lose, I decided to make the bearings from pieces of aluminum that would fit tightly onto those hardened steel rails. Now, this is not going to be long-term durable for a machine that's being used every day, but I anticipate that I will not be using this machine very often. Actually, I'll be using it, maybe once a month, if that. So I think this will work out. And to hold those bearings in place perfectly, I milled a slot in the gantry side. This is the original gantry from the Stepcraft. And here you can see how it fits on that hardened steel rail. And we'll call that breaking rule number 1. Breaking rule number 2 was to not use ball screws. Instead, I decided to use regular threaded rod. This is 3/8 by 16. And the nuts that I'm using are actually blocks of ultra-high molecular weight plastic. That's that very slippery plastic. And I made them extra long, and I didn't tap them out with a tap. Instead, I used the threaded rod itself to cut the threads so that there would be no backlash whatsoever. And in this picture, you can see how it all goes together with that aluminum bearing on the guide rail. Lots of grease will be going on there to keep that working smoothly, and the threaded rod lead screw in the plastic nut. For the X-axis, I once again used one of the old Y-axis rails, cut it in half, and then I ripped it down the middle so that I could have a linear bearing guide on the top and one on the bottom. And you can see that in this picture right here with the machine partially assembled. So I'm reusing the old stepper motors, but once again, I didn't have couplers that would mate those to the 3/8 inch threaded rod. So once again, I printed my own. And very much like the big CNC, these have held up perfectly. So the X-axis is in 2 pieces, and to join them together and add a lot of stiffness, I've got this big, chunky aluminum rail that's going to be screwed on solidly and bridge the gap between the 2 parts. I'm drilling and tapping for several number 10 screws. Now for the bed, I want to use that 1/2 inch thick plastic that I used on my table saw. I bought a full sheet of it a few years ago, and I had some left over, and I thought this would be the perfect material because it's waterproof. But before I could do that, I had to add ribs to support it, and I'm using 3/4 inch Baltic birch plywood for that. I cut the plastic to size and made sure that it was square, and that will help square the machine, slid it in place, and drove screws into those ribs to hold it down. Before I went any further with the build, I had to check to make sure that the bed wasn't twisted. And the easiest way to do that is with the crossed string trick. That's where you take two strings from both rails, and where they overlap in the middle, they should just touch. And that means that the rails are coplanar. So the next thing I did was I added some strips to the edge. The idea here is to make a surround around this bed to contain all the cutting. This will be for cutting metal, like I said before, and it will use coolant. So the idea is to try to keep everything within the cutting envelope, and if it's wet, it shouldn't fly up. It won't be a dusty operation. In other words, it shouldn't need a full enclosure. Instead, I want sides on there that are about 6 inches tall. And once again, I made those from the same plastic I used on the bed. So with that much done, I could hook up the motors and actually try it and see if it works. And yes, it did move. Very smoothly, actually. With any CNC machine, rigidity is very important. And to add some to the X-axis, I tapped out that big chunky aluminum rail on the end to drive in a 1/4-20 bolt. Then it was back down to the big CNC where I have installed the waiting pool that I talked about in my last video. And what this does is it acts as a way to contain the mess when I'm milling aluminum with coolant. The coolant in this case is just soapy water that I'm spraying on the parts. And the parts that I'm making here from 1/8 inch aluminum plate are for the Z-axis. As you can see, there's a lot of holes that I need to make in these parts. And it's remarkable how perfectly everything lines up. You can do this by hand, of course, with traditional tools, but you can't beat the precision of the CNC. As I went through the process of building the CNC, I was taking the time to try to make sure that everything is square as it could be, knowing that I would have to adjust it in the end, but getting it close to begin with. Now what I'm doing here is I'm actually tapping the holes that are in the linear rail so I can drive screws through those aluminum plates that I made into those rails that I'm going to cut the length and use on the Z-axis. And you might be saying, why are you using such chunky ones on the Z-axis when you went with the smaller ones on the Y and the X? Well, the reason is that these are solid hardened steel, and they'll add a lot of strength to the Z-axis that I don't have to do with aluminum. So I can get away with the 1/8 inch aluminum plate that I'm using. I got 2 layers of 1/8 inch aluminum plate here, the same size, and they have clearance holes for the heads of screws that hold them in place. And like I said in the last video, I'm designing all these parts with FreeCAD and using that to program the tool paths to cut it out on the CNC. And here you can see the Z-axis moving once again, 3/8 inch threaded rod for the lead screw, that white plastic for the nut, and another 3D printed coupler. And for the Z-axis, I'm using the same arrangement, 3/8 inch threaded rod and the ultra-high molecular weight plastic for the nut. This is another piece of 1/8 inch aluminum that's 12 inches long that gets screwed onto those chunky linear guide rails. And that's where those tapped holes come in. And once again, it is remarkable how well this lined up. I've got just enough clearance for the screw to fit into those holes in the plate, and they line up perfectly with the holes that are in the rails. The carriage bolts that I'm putting in here that fit in those slotted holes are for the clamps for the spindle. And I cut another piece of 1/8 inch aluminum to double up that area right there where this spindle will be. Now the spindle clamps that I'm putting on here are 3D printed, and they are for a router that I was originally going to use. To mount the motor on the top of the Z-axis, I've got a piece of 1.5 inch aluminum angle that I notched out, and now I'm drilling and tapping holes for screws that will hold on the motor mounting plate that I'm cutting from an offcut of one of the end rails off the Stepcraft. And once again, I'm doing this in the waiting pool on the big CNC. I can get another one of those 3D printed couplers slipped onto the lead screw, tighten up the screws, and get the mounting plate put on loosely so that I can adjust it after the motor is in place. I made slots for those screws so I could adjust it, but to lock it in place, I'm going to drill 2 more holes and tap right through those holes so that the screws will keep that plate lined up. And here's the router that I was going to use, and I'll tell you later why I didn't use it. And with that installed, I thought it would be interesting to put the timing bar on there to see how far out the whole thing is. And actually it wasn't that bad. Certainly nothing that can't be adjusted with shims. The bearings that I'm using here are from rollerblade wheels. They fit on a 3/8 inch shaft almost perfectly. And once again, I'm 3D printing the housing that the bearing fits in. And more 3D printing here with the bracket that holds the Z-axis limit switches. This one in particular has the switch on the bottom and on the top. I had to add a block to the plate that would contact the lower limit switch to set the upper limit of the Z-axis. More 3D printed parts for the limit switches. I actually glued this in place with super glue to hold it on until I could drill and drive screws. With the majority of the mechanical fabrication done, I moved the CNC down to what I'm calling hobby room number 2 and started working on the electrical. I've got a 10 by 10 by 5 electrical box that I drilled holes in and 3D printed grommets that fit in those holes for all of the wires that will be going in that control the CNC. What I got here is once again from the Stepcraft. It's a DC to DC converter. It takes the 30 volts from the main power supply and brings that down to 12 volts to run the limit switches. And I'm just going to super glue that in place. And then I can get the wiring done. That is tedious work. That took a long time. And if there's one thing that I've learned about wiring stuff like this is to be very careful. Because one slip up and you've ruined something that you're going to have to pay to replace. Luckily, I didn't make any mistakes. Now the board that I'm mounting the enclosure on is not screwed to the wall. It's actually screwed to the piece of OSB that I've set the CNC on. And with that mounted, I can properly run the machine for the first time to use that router to flatten the bed. And here's where I discovered the problem with the router. It vibrated too much and it was really loud, way too loud for the room that I have this in. So I decided to take the original spindle from the big CNC and mount that on this small CNC and use that instead. And here you can see it in action. I'm actually making new clamp parts from 1/4 inch aluminum for that spindle to replace the 3D printed ones I had that are a little bit too flexible for this kind of mounting where it's held only in one place. And this went very well. As you can see, I'm once again spraying on soapy water to use as the coolant. Eventually, the idea is to set up a flood coolant system for this. But in the meantime, just spraying it on there works fine. And the clamp is made up of 3 layers of 1/4 inch aluminum, cutting them all out at the same time. And then I can put them together using the holes that I made in them to line the parts up. And you might be wondering why 3 layers of 1/4 inch? Well, I don't have anything thicker. I bought 2 sheets of 1/4 inch aluminum to use on a few upcoming projects. The slots that it's milling right now are for the 1/4-inch bolts that hold it onto the Z-axis. And the parts came out really good. And I'm happy to say that the enclosure worked perfectly as well, keeping everything inside. Now to put these together, like I said, I'm using pins in the holes that I milled in the parts to line them up. And I'm using super glue to keep the parts together until I can get bolts in there. And here's a verified I build it tip for using super glue. Lick your finger and wipe the part that doesn't have the glue. That'll make it moist, and when you put the parts together, that moisture will help the glue cure. With that done, I can get it put on, and I also 3D printed the cap for that because most of the holding strength will be in the aluminum part anyway. And the washers that I'm using here are the ones that I cut in the last video from 1/8-inch steel on the big CNC, but they're temporary because what I want to do is cut a plate that will cover the end of this cap and add a lot of strength. And that'll be my first steel cutting test on this machine. Now the blank that I have here is not big enough for the part that I'm cutting out, but it's close enough. And basically what I'm trying to do here is test the machine and see how it works. And yes, it cut through that 1/8-inch steel like butter. Now with that done, I cut another piece of that 1/2-inch plastic for the spoil board on the CNC, and I got that put on the machine to mill out some pockets for regular 1/4-inch nuts to put in there for hold downs. I don't have any threaded inserts, so I'm going to do this instead. And it starts with a hole that goes all the way through, and the pocket gets milled out so that the nut has to be pressed in there, nice and tight. Then I can flip it over and screw it down. Make sure that the screws are countersunk below the surface because once again, I need to flatten this as well. And if you're wondering about the working area of this, it's roughly 16 by 16, which is more than big enough for everything that I want to cut on here. Okay, so what I'm doing now is I've got a very pointy bit in the spindle and I'm cutting grid lines in there. However, this is where I started having problems with that spindle. It started cutting out. And I know the sound, it's worn brushes. So I took it off and I opened it up because, you know, that's what I do. I take things apart and I had to look at the brushes. They looked okay, but they seemed a little bit short. And when I turned on the machine, they were sparking. So that signed the death warrant for this fairly expensive spindle. Now, brushes are available, but very much like the other parts that are available for this spindle, including a new collet that I needed. And the reason why I didn't want to change bits on this one is that they are available to Europeans and I can get them here, but the shipping would be astronomical. So that forced me to change again, this time to the cordless Makita router. And you might be saying, cordless, how's that going to work? The batteries are going to go dead while you're running it. And while that's technically true, I can make it so that each of the tool paths that I run are individual and not long enough to drain the battery. So I can have a battery charging while the other one's in the machine running. And when that particular piece of machining is done, I can swap out the battery for a fresh one. So with that change, I had to once again flatten the bed because really what I was trying to do here was get rid of those grid lines that I had already cut because they weren't perfectly lined up. However, they were close enough that I just took a skim off and then the new grid lines that I cut lined up almost perfectly. The grid lines are there for rough positioning of the parts. And the first thing that I had to do was make some proper hold downs. And I decided for now to make those from pieces of oak. And what I'm doing on the CNC is I'm making the slot. Now I programmed this tool path for cutting aluminum, and that's the reason why it's not being aggressive. But it still works and it still gets the slot cut. So I got the machine working flawlessly. I thought it would be interesting to do a project with it, not something I'm going to throw away, like that spindle clamp. Last year, around about this time, I designed and 3D printed base plate for the trim router. And the thing about this base plate is that there's a cutout in here for my insert set. Fits in there perfectly. Okay? Now, the problem with 3D printed, everything lines up perfectly. That's good. But the first one that I had of this was a white ABS one, and I dropped it on the floor of my shop, and it broke the corner off, making it, well, rendering it useless. Because you're using the outside as well, because the outside is concentric with the inside, which is concentric with this bushing area on the bushing. So I thought it would be interesting to take the exact file that I designed in FreeCAD and make one from aluminum. And the first operation is to drill the 4 holes for the mounting screws, but forgot that I need coolant here, and the end mill broke. So I changed it out for a new one, and this time I didn't forget the coolant. And as you can see, it zips down through that 1/4-inch aluminum like it's nothing. Now this is interesting because I'm cutting those countersinks with the regular end mill and stepping it up, and it actually turned out really good. It took very little time and it's very smooth. Speaking of time, after just 3 minutes of milling, I decided to change the battery again, even though it wasn't close to dead. The next operation cuts the stepped hole in the base plate for the insert to fit into. And that cut cleanly as well. And the final operation is to cut the outside of the base plate. And once again, I did all of this design work, including the work to create the tool paths with FreeCAD. All right, so the only thing left to do is to put it on and see how it fits. When I designed the original, I was very careful to accurately measure the hole locations for all of these screws, and they're very specific for this router. And it's good to see that these ones are lining up perfectly. And I'll have a much more rugged and durable base plate and then the 3D printed one. Anyway, I hope you enjoyed that, and you'll see me in the next video.